we want to discuss. Okay. Friction. What is friction? This is a type of force which occurs between any two bodies. Okay. Real life, whenever we are discussing the forces or the interaction between two surfaces, when you are sliding one surface on another or you are rolling one surface on another, all types of surfaces, between them there is a friction force. What is friction? The friction is an opposing force to the motion of the object. Okay. So no matter how smooth you make the surfaces, there will be still some amount of attachment between them. Okay. Like there are, let's say, sometimes you may feel that the wheels of your car are not doing that great. There is some kind of friction. You are hearing a little loud sound from the wheels of your car. What you do is that you take this to mechanic and the mechanic applies some lubricants there. Then after that, the sound is reduced by a fair amount, but nonetheless, there is still some sound, right? And that some sound will always be there. If you buy a car from the factory even, right? So brand new car will also produce some amount of the sound. And that sound is just because there are rolling surfaces on top of each other and they are producing the sound. So the friction, in a nutshell, it is always there, and we are experiencing in our daily life. What is the flaw between this force when we just say that F equal to ma, Newton's second law? There is a force which we talked about that in the chapter 5. What was the problem in that? The problem was when I said this is the block and I applied the force F and it produced acceleration. What we had neglected, that it doesn't matter how heavier the object is, if I apply any amount of force, I will be able to produce acceleration. So by using this law as it is, it just potentially implies that no matter you apply your force to this entire building, you will be able to move the building by some amount. But in real life, whenever we are seeing it, this is not true. And what is we are missing in this equation? That was the friction which we want to include here. Another is that there was the Newton's first law when we said an object, if it goes in motion, it will stay in motion forever, right? So that is not true, because our daily observation is that whenever we throw something, it goes up to some extent, but if it eventually slows down and stops. So there is some opposing force which is taking the energy from our object, and that is the friction force. So therefore, this friction force we want to include in this chapter. So what is the friction again? Here we will be at the 3-4 slides which I'm discussing. From now on, it will be just between the frictions and also the types of the frictions. That's all I want to discuss and build up this idea and then solve some problems based on it. So suppose that there is a block and the block is sitting on top of a surface, okay? Like as we are seeing here, the block is sitting on top of a surface and there is no attempt at sliding, like you are not applying any force to it. Just you are observing the block is sitting on top of a table. If someone asks how much is the friction between the block and the surface, the answer is obviously 0 friction, because you are not applying the force and therefore there is no counter force to your applied force. So therefore the friction force is also 0. Now, what if I applied some force to it? What will happen? If I applied my force F into it, as we are seeing in this slides to the left side, then there is an opposing force that starts to appear, and that is to the right, which is indicated by the lowercase f and with the subscript s. The subscript s, it means that the static, it is indicated the static friction, and this friction we always indicated by the lowercase f. So if my applied force is to the right, to the left, the friction force will be to the right, and vice versa. If I apply my force to the right, then the friction force will be to the left. So it will be always in opposite direction of the motion, okay, or attempted motion. What if I increase my force even more? What will happen? Well, if I increase my force even more, the static friction also increases because it is not letting the body to go. So the static friction is completely countering my applied force. So it will be again equal to my applied force but opposite in direction. Okay, until the body start to move, the applied force and the friction force always going to be equal. Okay. Now what happened that if we increase our force even more, what happened? Well, the static friction gradually increases and completely countering. Okay, no matter what. If the body is at rest, the static friction is equal to the applied force again. Finally, if my applied force was even more stronger than the force friction, then what will happen? That the body will start to move because of this equation here. The F net is equal to MA. If the net was always, the net force was 0, which is the F1 minus F2, if these two forces were equal, always we will get the net force equal to 0, and therefore the acceleration in all those objects will be 0. But if my applied force, suppose that is F1, if that started to be more than F2, we are getting some non-zero value. This will be not equal to 0, some value, some positive value. And once we get that positive value, we put that positive value here, we get acceleration because the mass of the object is there, it's not 0. So there is some mass of the object and some positive value which gives us acceleration. Okay. So, but now what you see in this line, that the force which we start to talk about now, we change the language. In the previous, when the object was at rest, we said static friction. When the object started to move, we started to use the word kinetic friction. Now the name we'll be using kinetic friction in motion. To maintain the constant speed, reduce the applied force to F, force to match the weak frictional force, the kinetic friction remains the same. Well, you started to see the language that we move from the static friction to the kinetic friction. But now in the kinetic friction, what happens that the kinetic friction does not depend on your applied force. The static friction does matter on your applied force. Okay, if you are increasing your force, the static friction also started to increase. While the object is in motion, there is just a fixed amount of kinetic friction. It almost stay constant, and then that's it. It doesn't depend how much force you are applying now, okay, or how much weaker force you are applying. As long as your applied force is more than the static kinetic friction, then the object will be kept in the motion state. One thing to note here, just note the final line. The kinetic friction is always less than the maximum static friction, not maximum, not just static friction, but maximum static friction. In the next slide, I'm going to elaborate this point a little more. Here, the block and the force, the interaction which I have mentioned, and accordingly there was the friction between the two surfaces. Those interactions we had mixed, we talked about. Now I'm going to break them down. You are seeing the diagram here. So let me put this diagram from here to here, from this point, which is the 0 time, until some fraction of time. Okay. As long as you are applying your force, you're continuously, the static friction is going to increase as your force, applied force is matching. Okay. It is the situation like this. You guys just watch my video here. Let's say this one hand is the surface of the block, okay? And this next hand at which you are applying the force. What usually happens is that you are trying to move this block away from you. What you do, when you are approaching to it, first your finger approaches to the object, so some amount of force applies on the object, and then accordingly, if you are increasing more force, then your entire hand touches the object, and kind of, which is also showing that this amount of force you applied, and accordingly the shape of your body also changes with respect to that. Okay, so this is from the 0 seconds all the way to this maximum. It is almost a linear line. It's not exactly linear line, but almost linear line. It goes like this. So you are increasing your force, but the object doesn't go. It is still maging. Okay. So this entire line from the zero until this maximum point, that is the maximum static fraction. But you may have noticed, like you are moving a table inside your house, and the table is a heavy table. Initially, you may feel a little bit difficulty to move this. But once they start to get into motion, then it is relatively easy to move. Okay? Like you can slide that easily. But the initial breaking point, bringing that into the motion, that is the difficult. And that is explained by this physics here. Because initially you have more friction and the maximum static friction is reached. After that, you break the bonding between the two surfaces and the friction force accordingly drops down. So this is the kinetic friction. Look at this kinetic friction. It is almost a constant line, horizontal line, right? And the maximum friction, the maximum static friction is here. So you see that the previous line which I mentioned here, the kinetic friction is always less than the maximum static friction. So the maximum static friction is up there. Okay, that's what I mean. This point is the maximum static friction. The rest is just called static friction, and it is the kinetic friction will always be less than that. Okay. The magnitude of the static frictional force increases when the force is applied, which we already learned in the previous case, and also the relative motion between the two bodies and the contact surface occurs. Then there is a kinetic friction, which we already studied in the previous case. Okay. The last point is again related to the last part of the block. The magnitude of the kinetic frictional force is less than the maximum magnitude of the static frictional force. Either using saying this thing like maximum magnitude of the static frictional force, or you just say maximum static friction. Okay, because I will be emphasizing a little more the vector nature of the two forces. Do you guys have any question here? So that we, if you have any question, I can answer that. Otherwise, we move on to the other chapters.
I have a question.
Yes. Okay.
When does the body will face the static friction? Is that when the velocity is zero, or when acceleration is zero?
You know that the static means rest, right? Static. So whenever the object is at rest, then the associated friction, we will be calling it static friction. So in that case, the acceleration as well as the velocity of the object, both of them are zero.
Okay.
Yeah.
So if the acceleration is zero and the velocity was something not zero, so there won't be static friction.
When the object is in motion, then no matter whether the velocity is zero or the acceleration is zero, okay. Sorry, not the velocity, but the acceleration is zero. If the acceleration is some constant amount, any other amount, okay, or variable, in that motion state, the associated friction, we will be calling it kinetic friction, because now the object is in motion. Whenever it is at rest would mean velocity zero as well as acceleration zero. We are not discussing like the velocity is zero or the acceleration non-zero. Even though the object is rotating in a circle, but if it is sliding on top of another surface, there is a friction in there. Okay.
Okay, thank you.
Yeah. So.
Sorry,
yes.
teacher.
Yes.
Okay, so there's a force of friction, right? There's a point where it breaks, which is when it's not at rest, right?
Yes.
When it starts moving.
Yeah.
Is that breaking point similar to every object, or is it affected by its mass?
This is definitely affected by the mass, and also it does affect on the different surfaces. Like you are riding your car, you may have not seen the steel wheels for your car. It is always the rubber which is in connection with the road, because the friction between the rubber and the road is more than the steel and the road. Okay, So therefore, you are choosing the kind of surfaces based on your material sciences. You are choosing the surfaces in which there is more friction. So from one object to another object, it does matter, one thing. Second thing is the motion, it also does matter. And the heavier the object is, the more friction it will be. Like, for example, your car has the rubber wheels, and a big truck has the rubber wheels. So between the big truck and the road, there will be more friction as compared to your car in the road, because the big truck is now heavier. So for the same material, the mass is a big factor. For the different materials, material to material, the friction, there is another coefficient which I will be introducing in this slide or in the next slide. Then you will see, yes, the surfaces also matters.
Okay. And I
Yeah.
have another follow-up question to that.
Okay. Yeah.
The reason why it's easier to move the object after its initial movement is because there's an additive force after, like additive force. Like if I let it go, it's gonna continue moving, right? Sometimes.
Yeah.
Yeah. Is it the reason why it's easier to move?
There is another thing between that. Let me just briefly talk about that. We don't need to get into the details. For example, you are putting into two hands like this, right? So you are seeing that your one hand and the second hand, both of them are a little bit rough. If you put them on top of that, you will be seeing a fair amount of space between them. Not all points between your hands are joining or touching each other, right? So wherever the two hands are touching each other, these two surfaces will be kind of trying to form the bond. Okay, like you are having the table on top of the floor, and this floor, wherever the wood is touching the floor, it will be trying to form a bond, like just the chemical bonds or the physical bonds. These are the different kinds of bonds that will be formed. So this is called a cold welded. For example, you are seeing the weld, you are already familiar, like you are putting two metals on top of each other and you are heating the surfaces just to form the weld between them. So this is called cold welding. Whenever you are putting the one surface on top of another, with the passage of time, it kind of form a specific bond that is called cold welded. And when you are trying to break them away, the initial breaking point is difficult. Afterwards, since the object comes into the sliding state, now there is not enough time allowed for the two objects to settle on top of each other and form that kind of core bonding. So there is no core welding between the two surfaces afterward. Okay, that's why when you move something into motion, it is easier to move compared to the initial breaking point. That's one of the reasons.
All right, that's very clear. Thank you.
Yeah. So the frictions, we are discussing the properties of them, and some of them will be a little bit repetitive of the last two slides, but here I'm going towards the formulation, so I want to put them in the formulas. So property one, if force F attempts sliding but the body does not move, the component of the force that is parallel to the surface is balanced by the static force, which we know it now. They are equal in magnitude and is Fs directed opposite to the component of the F. So here I have this block and I applied my force to it. Let me remove this because I'm trying to discuss this a little bit. So here, if this is the block, I applied my force in this direction, then the friction will be appearing in this direction. So this is completely in opposite direction to it. But what if I applied my force with some angle with respect to the horizontal? This is the force F, and it is making an angle theta. We know it is equal to F cosine theta, okay? So this friction force will be now based on this cosine theta, not the sine theta, because it is completely independent of the sine theta in this situation if it just keeps moving in one direction. So therefore, we are saying the same component, which is opposite to the friction. This is the second property. Without any proof, we are providing you these two equations. One equation is for the maximum static friction. This situation, this equation is valid if and only if we are discussing the peak point of the static friction. And the peak point by that I mean this point. Okay, here we have this point. like this. The equation is just valid only for this point, okay? Just the point which I have made it red now. This equation which I'm showing you, it is not valid for this region, not at all. It is only valid for this maximum point. So always, whenever you are applying that equation, you should be looking at the language of the problem. If they are saying at the verge of sliding or something like that, then you can apply that equation, otherwise not. Okay. So this equation for the maximum static kinetic fraction, here you are getting the mu. This is the mu now, which is the coefficient of the static fraction, and this Fn is the normal force. Okay. One thing to note about this, that whenever I'm putting this block again, just look at the whiteboard here, guys. One thing to note about this, that if I'm applying my force in this direction, we know the friction appears in this direction, okay? But we are discussing the normal force. So if this was on top of the table, we know that the normal force of on the object is upward, while the weight of the object is mg, that is downward. Now look at the equation. The equation we are getting it is Fs is equal to mu s, okay, and Fn. The direction of the Fn is to the plus y-axis. The direction of the Fs to the negative x-axis. So mu s itself, it is a scalar quantity. We have learned that if I'm talking about the vector A, if I multiply this with the 3 is going to only change the magnitude of the 3, not the direction of the vector A, right? But here I multiplied this quantity with the scalar, but the direction has changed. What's going on here? Can someone tell here something? Is this equation which you are seeing, does it satisfy the vector law or the vector rules?
Doctor, it's because of the mg defines how much the fs is.
Yeah, but the thing is, one thing which you need to know. Yes, please go ahead.
Because it does not change the value. It is a vector times the.
That is the thing. That's what I want to emphasize here. If your vector A was this and you multiplied with 3, it will be just 3 times of this. But the direction of this is going to remain the same. Direction will not change. Here we have this. Yes. Fn is a vector which is pointing to the plus y direction, and we multiplied it with the scalar quantity. We should be demanding that the magnitude should be increased vertically, not in the x-axis, and especially which we are seeing the negative x-axis here, right? So the short answer for this is the equation that we derive for the static fraction as well as for the kinetic fraction, they are not vector rules. They are not vectors equations. They do not satisfy the vector laws, okay? Like in terms of the vector directions, because of the normal force and the friction force. Otherwise, whenever we are putting them in the equation, subtracting and adding, we can look for that, okay? Another thing is that the kinetic fraction, we mentioned that the kinetic fraction arises when the two surfaces are in motion. When they are moving on top of each other, there is a kinetic fraction, and the equation is this. Look at the static fraction equation and the kinetic fraction equation. The only thing different between the two equations is the coefficients. Coefficients of the kinetic fraction is mu k, and coefficient of the static fraction is mu s. And mu s is always greater than mu k. Whenever we are talking about any two surfaces, the mu s is going to be greater than mu k. These are the two equations. You are seeing them side by side, and here I'm again trying to emphasize these are not the vector equations, because the direction of the Fs and Fk, they are opposite to the applied force, but the normal force is perpendicular to the surface. So we should be careful just saying things like that for the vectors.
Teacher,
yes.
One question.
Yeah.
The mu s to the mu k, how do we get it? How do we derive it? Where do we get it?
I'm solving problems on that. We will be able to derive them, but normally for the experimental purpose or for your engineering purposes, whenever you are talking about the two surfaces, it's more like empirical equations. Like I'm having two surfaces in my office, and I'm trying to look for the friction between this wood and this, and then this wood and the other side. I definitely, by experiment, I turned out that this side having more friction as compared to the wood against the whiteboard. So one is the experimental approach, another one is empirical. We will be approaching to that, the theoretical, sorry. So we will be approaching to it theoretical in the few problems down there. Checkpoint 1. A black lies on a floor. A black just lies on a floor, like your laptop lies on your table. What is the magnitude of the fractional force on it from the floor?
0.
0. Because you are not applying any force, and accordingly there is no friction force between your laptop and the surface. Okay. If the horizontal force of 5 Newton is now applied to the block, but the block does not move, what is the magnitude of the fractional force on it?
5 Newton.
5 Newton.
5 Newton, because now it is completely matched and countered. Okay, so the static friction is matched by the applied force. If the maximum value of Fs max of the static fractional force on the block is 10 Newton, maximum static friction is 10 Newton, will the block move if the magnitude of the horizontally applied force is 8 Newton?
No.
No.
No, because 8 Newton is less than the maximum static kinetic friction. Therefore, it will not move. If it is 12 Newton, what will happen?
It will move.
It will move. Okay, what is the magnitude of the fractional force in part C? How much is the friction force in the part C?
10 Newton.
10.
No.
It's less than 10.
2.
So the friction force is exactly equal to the applied force because the object was still at rest. So as long as the object is at rest, the static friction force is equal to your applied force always. Okay.
Teacher, I don't
Yes.
think that was kind of. Could you elaborate more on the last one, on the last question?
The last one is that it says this maximum static fractional force is 10 Newton, right? So the object will not move until your applied force is 10 Newton. Okay, so that's what it means. You applied your force 8 Newton. So the static friction is equal to 8 Newton, which is less than the maximum static friction, right? Recall that. Here, you are seeing this slide. This is the maximum static friction. They are saying this is the maximum static friction for you, which is 10 Newton there, okay? But you applied a force somewhere here. The object will definitely not move because your force is less than the maximum static friction. When they are asking you, how much is the frictional force, you say, the force which I have applied equal to that amount is the frictional force. You got it?
Yep.
Okay. Always remember that slide, the graph, because we will be using that in some problems. And the record for a longest skid marks on a public road was reportedly set in 1960 by a Jaguar on M1 highway in England. The marks were 290 meters long. Assuming that mu k, which is 0.6, the car's acceleration was constant during the braking. How fast was the car going when the wheel became locked? When at the end of its brake, we definitely know the car came to a stop. So we know the final speed is 0. What they are asking is that how fast the car was moving, they're asking for the initial speed, okay? But in order to determine the initial speed, do we have any acceleration? Do we know acceleration here?
No.
The acceleration. No, I don't know.
Okay. This is the road, and here you have this car. The car is going in this direction. So by the time you just applied the brake to it, then the engine acceleration is gone. Like means the engine is no longer providing any force to your car, okay? Because you are controlling the car now. So after that, if the car is going in this direction and it covers 290-meter distance and it comes finally to a stop. So V initial, how much it is, while the VF is 0 right there. We want to determine how much is the acceleration. So when you apply the brakes, the engine acceleration is off, like there is no acceleration coming from the engine now. So you just applied the brakes. What kind of force is there on your car?
Fraction.
The friction force.
So that's the only friction because your car wheels are locked. So that's the only friction. So if the car was moving in this direction, the acceleration is this direction. Okay, that's the kinetic friction. Now we know that the kinetic friction Fk, since due to this the object was moving or decelerating, you can say that this is the deceleration. And since this is the deceleration, you can also the acceleration direction would be in the opposite direction because of the deceleration. This is one equation by the Newton's second law. Turn off your mic, guys. They're producing a little bit more. Okay, here you have Fk. Yeah, here you have this mu k. Mu k is ma, and you also know that the mu k equation is equal to mu k Fn. We also learned that in the previous slide. Mu k Fn is another equation for this. So here, when I see that the car is already on the road, that there is a fair amount of weight of the car, which is mg downward. As a result, there is Fn upward. So when I was resolving the forces along x-axis, I got Fk equal to ma. But when I'm resolving the forces along y-axis, I'm getting that the Fn is equal to mg. Because these two are completely countering each other. Okay, so Fn is equal to mg. Now what I do is that if this is equation 2 and this is equation 3, I will just compare the two equations, mu k, and instead of Fn, I will put mg equal to ma. The mass of the car is gone from the equation. All I left with is the mu k and g. Mu k is given in the problem, which is 0.6, and g we know it is 9.8. So this one will give us acceleration, meter per second square, equal to a. Okay, so this is my equation 4. Now, since they're asking for the initial speed and the final speed, we know it. Now we also know the acceleration. Can you tell what equation we are going to use here?
V final squared equal V initial squared plus 2ax.
Exactly, that one. Yeah. Vf squared minus Vi squared equal to 2ax. Okay, the final is 0. I left with minus Vi squared equal to 2ax. We know this acceleration here, since this was a deceleration, I will be putting the negative sign. Whatever I get from here, I will be putting the negative sign there. So Vi under square root, just take the square root, it will be negative 2ax under the square root. Don't be afraid of this negative sign because this negative, the value of the a is also negative. So that negative with this negative will become positive under the square root. So it will be 2 times 0.6 times 9.8 times 290 meters. It will give us the initial speed. Do you have any question here? Okay, this is the solution which I provide there. Now let's look at this problem. In this figure, a block of mass 3 kilogram. Did I stop the attendance, guys? Just let me check that. Okay. Stop responses. Okay. Another thing came to my mind. Just would like to remind you. Did you receive any email from the university side asking about your midterm exam hall?
Yes.
Okay.
Yes, sir.
Yes, yes,
Okay. Did you guys respond to that?
yes.
Yes, you mean the survey,
Yes.
right?
Yes, like you are choosing your center, which city you want to take
Yeah.
your exam in.
Yes,
Okay.
yes.
So if any student has not responded to that, kindly respond to that because it's a very serious matter. University wants to make a decision based on your feedback. So you need to respond to that survey. I'm also sending you a reminder after this class and work on that, okay? Tomorrow is last day for that. Yes.
Teacher,
Yes.
for those who live near the university, do they also have to fill the form?
Yes, all students need to respond to that. If they live near the university, then they will be choosing obviously a hall, exam hall inside Dhahran. And other students who are living in Jeddah or somewhere else, then they will be choosing the hall wherever it is convenient for them. But respond, okay?
Doctor, when did they say?
That is due tomorrow, but you need to respond to that. And also
I
the
didn't
midterm
get-
exam, the midterm exam date is not decided yet. If you are asking about that, it is not decided yet. But just you need to respond to that now. Okay. Let me continue with the problems here. And this one, this figure, which is the figure A here, you are seeing a block of mass 3 kilogram slides along a floor while a force F of magnitude 12 Newton is applied to it at an upward angle theta. The coefficient of kinetic friction between the block and the floor is mu k, that is 0.4. And notice that the coefficient of kinetic friction and static friction that have no units, okay? We can vary theta from 0 to 90. What theta gives the maximum value for the block's acceleration magnitude A? So look at this problem because there is a little bit trick involved and we need to learn that now. Lots of problems will be based on this kind of trick. So there is this horizontal surface, the block is on top of it, and a force is applied to it, force here, and that force is making an angle theta with the horizontal. And when this is moving, we know there is a friction between this, since the object is going along, is sliding along the this x-axis, let's say, then the friction force is going to be in the opposite direction, mu k, fk. Here, what we need to do is to dissolve this force because the acceleration is produced by a component of the force, not the entire force. So this is going to be f cosine theta. And this one is another component of the force. This is called f sine theta. So these are the two components of the force. Okay, we dissolve it. Now, there are two forces which we need to bring in. What are those two forces?
Fj and Fn.
Okay, Mj is the weight of the block that is downward, and as a reaction, there is a normal force upward, Fn. Okay, these are the sets of forces which we know it now. Now, as a result of these many forces, the object is accelerating to the right side. So the acceleration direction is also this direction. So let's put your xy axis. This is the like this. This is your x and this is your y. Positive x, positive y. Okay. What we need to do is to resolve the forces along x-axis first and along y-axis later. And then all the forces to the positive x, we will be considering them positive. To the negative x, we will be taking them negative. Similarly, for the positive y, the forces will be positive. To the negative y, the forces will be negative. So let's take the along x-axis. F cosine theta is the force which is to the right side, it is positive, minus Fk, which is to the negative, we took it. Now, as a result of these two forces, the object is accelerated to the right. So, since the acceleration is to the right, therefore, I'm also putting the acceleration positive because it is to the x-axis. So, this is my equation 1. Now, here we also know this. Let's build up another idea on top, and then we will be coming back to it. We know this. We know that this Fk is the equation for the Fk is equal to mu k Fn. We know this equation because this is what we had derived. But I need to know how much is the Fn. Okay, that's the something which I also need to know. Now we also from the diagram we know the Fn is along y-axis. So now we are resolving the forces along y-axis. Can someone tell me how many forces we have along y-axis?
3 forces, Fn and mg and F sine theta.
F sine theta. So the positive side, the Fn is positive, plus F sine theta, it is also positive. And here we have the minus mg, which is to the downside. And as a result of these many forces, the object is not accelerating. So therefore, the acceleration along y-axis is 0. So we get it to 0 on the right side. Since I'm interested in the Fn only, therefore I'm rearranging this equation for that. Fn is equal to mg minus F sine theta. So this is my equation 2, this is 3. All I'm going to do is to combine, put equation 2 and 3 in equation 1. So this equation I can eliminate and we'll write the equation here. It will be Fn, F cosine theta minus mu k, and for the Fn I'm putting this mg minus F sine theta is equal to ma. This is the equation I wrote. Okay, this is what I have. This is the final product. Now, read the last sentence of the problem. They're saying, what theta gives the maximum value for the black acceleration magnitude A? What should we do now? If we are thinking that the A is maximum with respect to angle theta, what should we do? If something become maximum with respect to another thing, whenever you take the derivative of that with respect to that variable, it will be 0 because it is maximum. No further change can happen in that. Okay, so therefore the further change will be 0. So now I need to just divide this side by both sides by m just to isolate this a and take the derivative. So dA by d theta is equal to 0. That's what we get because it's a maximum. When we apply derivative to this one, F sine theta. So sine theta will be positive or negative?
I think negative.
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 Okay. And then we have minus mu k. This term is constant with respect to theta. It's a constant, will be 0. And from this term, we are getting it to be cosine theta. The negative sign, it will be positive. So here we get F cosine theta. Okay. Now rearrange this equation. We also see this, that the m I can take it out, theta I can also take it out, and just solve this for the mu k. When I solve this, this will be sine divided by cosine, which gives me tangent theta. Tangent theta is equal to mu k. And now we know that the theta is a tangent inverse of mu k. We get an angle from this. That will be the final answer. Any question here? Did you guys understand this problem?
Yes. How did you get the 10?
How did we get the 10? Because here you can, this is 0, you can throw this m out because it's common, and you also have the force. You can take the force common and take it out. At the end, what you will be left with it with the sine theta here minus sine theta plus mu k cosine theta equal to 0, right? So move this to the right side of the equation, what you will get?
Sine theta
cleared it.
equals
Mu k
Clear.
cosine theta, right? Then you divide both sides by cosine theta. So cosine cancels out from here, and this is sine by cosine is tangent theta. Okay. Guys, look at this problem. Because this is the last problem we are solving. A 3 kilogram block starts from rest at the top of the 30 degree incline and slides a distance 2 meters down the incline in 1.5 seconds. Calculate the magnitude of the frictional force acting on the block. So we know that in this case the block is just sliding down. There is no other force applied. So this is the incline, and there is this block. Okay, then with respect to the incline, it is making this angle theta. Now we need to resolve the forces. We already have learned the techniques that if this is sliding downward like this direction, then the fraction is going to be upward, Fk. Fk is going to be upward. We also know that this block is sitting on top of this inclined plane. As a result, there will be a normal force from the plane, which will be perpendicular to this plane, and that is called Fn. There is another force, which is the weight of the block that is downward, which is mg. Since our interest is to resolve the forces along the x and y, which are a little bit tilted coordinates, so therefore we need to resolve this mg in two components. One is the mg cosine theta, and this one is the mg sine theta. This was the technique which we had learned in the previous lecture. So we resolve these forces in this direction. Okay. Now we want to determine the frictional force. So obviously the force which we want to resolve will be along x-axis here, along the plane. Can someone put the forces here? Yeah, tell me the forces and what are positive and what are negative.
mg sine theta is on the negative x.
Okay, negative x. So mg sine theta.
Positive. Y.
What is to the positive?
Fk.
Friction.
Fk. Fk is to the positive.
Fractional
And
force.
the results
Acceleration
are
is the
sliding
negative.
downward. What is the
Acceleration and negative.
negative?
Ma.
So minus ma. That's what we got. Okay. Now we will take a little bit time and try to assess. Do we have everything here or not? And also whether it is logical to proceed in this direction. Okay. One thing we need to learn. That's one of the equation. We have it. Second is that we know that the force Fk can be written as mu k Fn. So resolve the forces along the y-axis. When we resolve the forces, we will see that Fn to the positive x-axis and the mg cosine theta is to the negative x-axis, negative y-axis. Do we have all the variables for this?
Yes, yes.
Yes, we have.
Okay. If we have all the variables, do we have mu k?
No, we don't.
We don't have mu k. So that's the sticking point. We are stuck there because we don't have it. So what we need to do is we stick with equation number 1 and we look at the known variables and unknowns. We know m, we know theta, g is known, m is known, and acceleration and the fk, these are two unknowns. Here we will be going back towards the equation set which we had applied earlier, like this. X, which is, we are considering it as x, v naught t half g t squared, right? They are saying that it is starting from rest. It is starting its motion from rest. So the initial velocity is 0. Again, we know that how much it has been sliding. It has been sliding for 2 meters. Half, and g, we know it is 9.8. Sorry. Guys, I don't need, I messed up here. This is not g.
Is it mg cosine theta?
A. This is A. This is A. This is A here. A, and we know the time is 1.5 seconds. 2 half 1.5. The only unknown here is the acceleration. From here we determine acceleration, which will be 4 divided by 1.5 square. Okay? We get the acceleration from here. Once we bring that and put this in the equation, one, the only unknown we will be seeing is the Fk. That's what we need to determine. Like this. With this, we are going to stop our lecture. Okay? Any question you have? Guys, any question?
Should we use the derivatives sometimes to solve the questions in this chapter?
Once in a while, whenever we are talking about the maxima or minima, we will be using the derivative. Okay. Therefore, the maxima and minima, there are other approaches we also used. But when they say that one variable is maximum with respect to another variable, then we need to use the derivative. Like, for example, they say that the acceleration is maximum with respect to that time. Then we need to take the derivative.
Okay.
Yeah. And the concept, if you ever got a little bit confused, that consider the derivative, consider a shape like this, okay? S-type shape. This is a minima. When you are at a minima, what is the slope here of the tangent line?
It's 0.
And when you are at maxima, what is the slope of the tangent line?
0 also.
0. So at maxima and minima, whenever you are taking derivative of with respect to some variable, that will be 0 just because at maxima and minima, the tangent line is just a horizontal line. Okay. Any other question?
Doctor?
Yeah.
Just one thing with the form.
What is that?
I haven't done the form. I was going to tell you when you closed it, but we started another question. I'm sorry. I forgot to do it.
Okay, when did you join? I'm going to download the attendance. So tell me the truth.
Yeah. I did join early. You can check if you want. I did join early.
Send me your comment here, the ID in the comments.
Thank you, Doctor. I'm sorry.
Doctor?
I opened the form for you, but you also need to send me the IDs. I will be matching the two. Okay.
Do we do the attendance again?
No, you don't need to do it. It's just if you claim that you were there and you missed it, I'm telling the form with. Yeah. Yes, you are asking a question?
Doctor,
Yes.